Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 25 on the subject of computer organization and assembly language programming. This is the closing session of the first half or the pre-mid part of the course, in which we have designed a full-blown 16-bit von Neumann machine called Hack Computer, capable of executing programs written in Hack machine language. The title of today's session is Design of Hack Assembler. So we are going to design a computer program called Assembler in C or C++ language, capable of translating a program written in Hack assembly language to its corresponding or equivalent Hack machine or binary language that can later be loaded in the instruction memory of Hack computer and executed by the CPU. And this is how we are going to proceed in today's session. First of all, we will try to understand what is the general concept of an assembler and how it works, irrespective of any specific language or hardware platform. Then we will have a quick recap of Hack machine language specification. We will see a demo of the available built-in Hack assembler having a graphical user interface. And after setting up the stage, we will design a basic version of Hack assembler that do not take care of symbols. Then we will design a two-pass assembler that will take care of all the language built-in symbols as well as the user-defined labels and variables. Then we will talk about implementing this assembler program in C or C++. And finally, we will translate our different Hack assembly programs using this command line based assembler to Hack binary programs, which can be executed on our already designed Hack computer chip running in the hardware simulator or maybe inside the CPU emulator. It appears that this will be a bit lengthy but informative session for you all. So let's start playing. Okay, let's see what is an assembler and how it works. Remember, in this part I will be talking about assemblers in general, that is not specific to a particular processor. So my dear students, an assembler is a program that takes as input a file containing assembly instruction as shown over here. Here the file name is swap.asm, and remember these instructions can be in Hack assembly, x86 assembly, ARM assembly, MIPS assembly, or maybe written for the open source RISC-V architecture. Now the task of the assembler is to translate these assembly instructions one by one to equivalent binary instructions and generates an output file, suppose swap.hack. Well, this executable file can later be loaded on the specific hardware platform to be executed by the specific CPU. And let me talk a bit about the format of these two files. Well, the source file containing the assembly instruction is a text file, and this destination file or the output file contains the bit pattern of executable instructions. The format of this file can be a binary format or a text format, and that is the choice of the designer. Okay, dear students, let us suppose that someone among us has written an assembly program and it is there in this file swap.asm, and this is the Hack computer on which we want to execute this program. But first we need to translate this assembly program in this file swap.asm to the binary program in the file suppose swap.hack. and this will be done by the assembler program. Now a $100 question is where this assembler program will execute. The answer is on another computer. So this is the other computer, maybe x86-64, on which we can write the hack assembler program in some high level language like C or C++. The final executable version of this assembler will take this swap.asm file as input and will generate this swap.hack file as output, which of course can be later loaded on this hack computer to be executed by the hack CPU. And so this is sometimes called cross compilation as well. That is the assembler running on x86 architecture and is generating the machine code for the hack architecture. So this way we don't have to write a bootstrap program in hack machine language that first translate this swap.asm to swap.hack. Rather, we write it in some high level language that we have already implemented on another computer. Dear students, before we see how an assembler works, let me say a few words about symbols in assembly language. And a symbol is actually a reference to some memory address. Other than the predefined or built-in symbols, an assembly programmer can use user-defined symbols in two ways. The first category are the label symbols. For example, consider this generic assembly instruction, which when executed will cause an unconditional jump to a location inside the instruction memory pointed to by this label loop. So this loop is a label symbol. The second category are the variable symbols. For example, once again, consider this generic assembly instruction, which when executed will load the value of the variable named weight inside the CPU register R1. And variable weight is actually a named memory location inside the data memory. Dear students, before an assembler generates the machine code, it needs to replace these symbols with appropriate addresses. For example, the symbol loop needs to be replaced with instruction memory address 127. Similarly, the symbol weight needs to be mapped or replaced with the data memory address 524. Now let us try to understand as to how an assembler resolves these symbols. Consider this code in some hypothetical assembly language, and also assume that as per the language specification, variable allocation starts from the data memory address 1024. And now let us try to resolve the symbols in this code one after another. The instruction at address 0 is I is equal to 1, where I is a variable. So as per language specification, I being the first variable is assigned the address 1024. So the symbol I is resolved with the address 1024. So we are writing 1 to memory address 1024, which is the same as I is equal to 1. Let us move on to the instruction at address 01. Sum is equal to 0, where sum is also a variable and is assigned the address 1025, assuming that every variable take just one memory location, and this is the second variable. So this variable sum is resolved and replaced with memory address 1025. The next line, loop colon, is a pseudo instruction where I have declared a label named loop, and we all know that a label is a user defined symbol which serves to mark the destination of a goto command. In most of the cases, an assembler will associate the address of the next instruction with this label of this address. So the assembler will assign instruction memory address 2 with this label loop. It will keep this in mind, and later over here at address 5 it will come across this label loop. So it will replace this label with the instruction memory address 2. Okay, so far so good. Let us move on to the instruction at address 2. If I double equals 101, go to end. Here I is a variable and we know its address is 1024. This end is a label, but it is yet not been defined. If we look at line number 6 over here, the label end is declared. So this end is a label which is used before it is defined, and this is called a forward reference. So we cannot resolve this symbol end over here. There are two possible solutions to this forward reference problem. The first is leave this label blank. When the definition of the label comes over here, then fix this. And the other solution is use a two-pass assembler. In the first pass, create the symbol table, and in the second pass, use it. Well, dear students, a two-pass assembler is an assembler that goes through the source file twice. In the first pass, it creates a symbol table for that file, and in the second pass, it resolves all the symbol references and generates the appropriate machine code. So a symbol table is a data structure used by an assembler or compiler to look up and resolve symbolic names with their corresponding memory addresses. Let us try to understand this with the help of some example. And this is the same assembly code with two variable symbols, namely I and sum, and two label symbols, namely loop and end. In the first pass, the assembler will go through this source file and generates a symbol table for this symbolic program. Moreover, it is assumed that variables are allocated to memory address 1024 onwards. So this symbol table will contain name, address pair of all the symbols in this source file. The first symbol is I, that is mapped to address 1024. Sum is mapped to 1025. This label loop is mapped to the next instruction address, that is 2. And this end is mapped to the next instruction address 6. So after the first pass is done, we have the complete symbol table with us. The next task is to do the translation. So dear students, since we have all the addresses of the symbols, so we can easily generate code without symbols as shown in this file. And if we know how to translate this code to binary, we could have done that as well in the second pass. Okay, so this slide shows you a bit of details of how an assembler works. What we do is we read the assembly language instruction from a file, we parse it, that is, we break the symbolic instruction to its underlying fields, we generate the code, we handle the symbols, and then finally we assemble. We combine all the binary codes into a complete machine instruction and maybe write this machine language instruction to an output file as well. And we repeat all this again and again until we reach the end of the file. Let us see these steps in detail one by one. Suppose this is the first instruction. Over here we have comments, and of course our assembler is going to ignore the comments as well as blank lines and white spaces. So this is the first instruction. We read this assembly instruction into an array of characters. Then we do parsing. We break symbolic instruction into the underlying fields. So we separate this load, separate this R1 and separate this 3, 5 over here. An assembly instruction may be separated by spaces, by commas, or maybe by other special symbols. The next step is the code generation. That is, for each field we generate the corresponding bits in the machine language. And suppose for load we have this table which says that the opcode for load is a 5-bit binary combination which is 11001. So we have written it over here. We do not know what this R1 stands for. Maybe this is a symbol. And over here we have a constant 35. And let's suppose as per the machine language specification, this constant has to be converted to a 8-bit field, that is the binary equivalent of 35. So this is the binary equivalent of 35 in 8 bits. And the next step is the symbol handling. What we do in that is we replace all the symbolic references with the numeric addresses. And for the time being, let's suppose that this symbol R1 is replaced by a 3-bit binary combination 001. And if there is an R2 over here, we could have replaced it with the binary combination 010. So these are the 3 encodings of the instruction given to us. And finally the last step is the assembly step, in which we combine all the binary codes into a complete machine instruction and write this machine instruction in an output file. So we have successfully translated this assembly instruction into its corresponding 16-bit machine instruction. So dear students, now we know what is an assembler and how it works. And before we start designing our hack assembler, let us have a quick recap of hack machine language specification. First of all, the A instructions. Its syntax shows that an assembly instruction that starts with @ symbol is an A instruction, and followed by the @ sign we can have a decimal constant or a symbol. So at 23, so we have a constant value after this @ sign. Well, to generate the machine code for an A instruction, we simply convert the decimal constant, this 23, to a 15-bit binary number, and in case of a symbol we resolve it. So here is the corresponding machine code for this symbolic instruction. Note that the most significant bit is 0, which is the opcode for the A instruction. Followed by the opcode bit, we have a 15-bit binary equivalent to the decimal constant 23. So after the A instruction, let us move on to the C instruction. And the syntax is shown over here. we compute, and then we either assign the result to some destination, or based on the computational result we decide to jump. And let us generate the machine code for this sample instruction d is equal to d plus a. So the first 3 bits over here shows that this is a C instruction. The 1 shows that this is a C instruction, and the remaining 2 bits are not used, so they are kept 1. You can keep them 0 as well. After this, we need to check out the computation. The computation is d plus a. We see this table. For d plus a computation, the 7-bit corresponding values are, we have a 0 for a, and for the remaining 6 bits we have 0, 0, 0, 0, 1, 0. So this is how it goes on. After the computation, we check for the destination. So in the instruction we can see that the destination is the register D. From this table we can make out the 3-bit combination for selection of the destination D register, which is 0, 1, 0. So after this we have 0, 1, 0, and finally we have the 3 bits for the jump instruction. And by seeing this C instruction, we know that there is no jump involved in this instruction. So if there is no jump involved, so the 3 bits for the jump should be 0, 0, 0. So this is the 16-bit binary hack instruction for this hack symbolic instruction. D is equal to D plus A. Let's see another example, and let's try to generate the machine code for at 17 first. So it's very simple. This is an A instruction. So we have a 0 over here, and this is the 15-bit binary equivalent of the constant 17. For the next instruction, the computation is d minus 1 as shown over here. The destination is null 0, 0, 0, and we know this is a jump instruction which says jump if equal JEQ, and the 3-bit combination for this is 0, 1, 0. So finally this is the 16-bit binary code for this assembly instruction. Well, dear students, this slide shows 3 categories of symbols in hack assembly language. First of all, there are 23 built-in symbols. Symbol R0 to R15 denote the virtual registers and refer to RAM addresses 0 to 15 as shown over here. The symbol screen and KBD refer to RAM addresses 16384 and 24576 respectively, which are the base addresses of the screen and keyboard memory maps already discussed in the previous sessions. And finally, these are the 5 built-in symbols: SP, LCL, ARC, this and that. They have not been used in this course. Moreover, remember dear students, all these built-in symbols are case sensitive. So this KBD in capital is this symbol, and if you write KBD in lowercase, this means something else. And in this file swap.asm, the predefined symbols used are R1 and R0. Now let us talk about the second category of symbols called labels. These are user defined and serve to mark the destination of go-to commands. In hack assembly, a label is declared by putting its name within parentheses, and later it can be referred to by preceding the label name with @ in the A instruction. And in this hack assembly program, we have declared a label AND over here. So the assembler will associate the address of the next instruction, that is 13, with this label, and it is just a coincidence that this label AND is referred to in the very next instruction. One last thing is the naming convention for labels, and the naming convention is use uppercase alphabets whenever you are going to name your labels. Now let us talk about the third category of symbols called variables. A variable symbol is a name used in an A instruction. If it is not already declared as a label, then it qualifies to be a variable. So the hack assembler will map it to some available data memory address starting from address 16 onwards. And in this hack assembly program, at instruction 3, a variable temp is declared. As no label with this name exists yet, and since this is the first variable, so the assembler will associate RAM address 16 with it. Later this variable is reused at instruction number 9, and since a variable with this name already exists, so no new variable is created, and the assembler simply maps the RAM address 16 with it. And one last thing is the naming convention for variables, and we normally use lowercase alphabets to name the variable symbols. Okay dear students, now we have a fair idea about how assembler work, and we have also revised our concept of hack machine language specification. So before we start working on the challenge of writing and designing our own hack assembler, let us first see the demo of the built-in graphical hack assembler that you can find in the tools directory already downloaded from the class Bitbucket repository. And this slide shows the GUI of the built-in hack assembler. And let's move to the terminal and give you a demo of this. Well, inside the tools directory, you can see the assembler.sh and assembler.bat file. You run the assembler.sh for Linux and Mac, and you execute the assembler.bat for your Microsoft Windows. Wow. So this is the GUI of our hack assembler, and let us load our source assembly file by clicking this icon over here from the folder 25. Let me load this swap.asm. So in the source file pane, you can see the swap.asm file having comments as well as empty lines. Moreover, you can see the A and the C instructions, and the sudo commands as well over here. And let us run it one step at a time by clicking this button, single step. Note that the comments and empty lines are ignored, and once we reach this first instruction, this is translated to the corresponding hack machine code. Note that since this is an A instruction, so the most significant bit is 0. R1 is a built-in symbol mapped to RAM address 1, so the remaining 15 bits of the instruction code is the binary equivalent of 1. Let me keep pressing this button. So every assembly instruction is converted to the corresponding binary 16-bit binary hack machine code. And finally, you see the entire assembly program is completely translated to its corresponding binary code. We can always save this machine code in some output file by clicking this save button, and let me save it with the name of swap.hack. So this is the file now containing the machine code of our 16-bit hack computer. So I think that is enough. Let me fall back to the slides. Okay, dear students, you should try to load and execute this swap.hack as well as other executable files inside the 16-bit hack computer chip that you have designed in this course. If you have not done so, you can use the CPU emulator available in the tools directory, which you must have downloaded from the class Bitbucket repository, so that hack machine code written in the swap.hack file can execute either on the CPU emulator or on the hack computer chip that we have designed in this part of the course. Okay, dear students, now the stage is all set, and I think we are ready to design the assembler for the hack assembly language. But once again, to keep things simple, let us start by designing our hack assembler that do not deal with symbols. And dear students, suppose this is some hack assembly program written by someone, and right now we don't know what is the logic of this program, and we don't need to know, being an assembler. To write an assembler in some programming language like C, suppose, I just need to open this text file and read it line by line. I will simply discard all the lines that start with double slash, which is a comment, or empty lines or any empty spaces within a line. And we can simply ignore them. For simplicity, let me ignore all these lines, and the resultant assembly file is shown over here, which do not have any white spaces. The next task is how to handle the symbols. And for simplicity again, assume that the assembly programmer do not use symbols. So instead of using these symbols, the assembly programmer has written the assembly program something like this. Note that the variable I over here is replaced with the RAM address 16, and the variable sum has been replaced with the RAM address 17. The built-in symbol R0 is replaced with constant 0, and similarly the stop symbol that was over here is replaced with the instruction memory address 20, and so on. So that means the assembly programmer is capable enough to use the memory addresses while writing this assembly program instead of using the symbols. So my dear students, the only task that the assembler now needs to perform is to translate these A and C instructions one after another. Do note that there is nothing else in this file containing the hack assembly program. Okay, so here are the 26 assembly instructions with addresses starting from 0 to 25. Note that each address contains some text, and we need to convert this text into a 16-bit binary code. So here are the 4 tasks we need to do for every instruction. That is, parsing the code generation. Maybe we can omit this for the time being, and then we need to combine or assemble. And let us start with the instruction at address 0, and that is at 16. First thing we need to do is to parse it, that is, break it into underlying fields. And since it starts with the symbol at, so that means this is an A instruction. So for an A instruction, we simply need to translate the decimal value into its corresponding binary value. There are no symbols in this instruction. So for the assembly step, we place a 0 over here because this is an A instruction, and then this constant 16 is replaced with the binary equivalent, 15-bit binary equivalent of 16, and this is of course 1, 2, 4, 8, 16. This is of course 16. Okay, now let me translate this second instruction, that is m is equal to 1. We need to parse it. So we have two components, m is equal to and 1. So we know this is a C instruction, and we know very well how to populate the 5 different fields of this instruction given this table. So this is how this is converted. The most significant bit is 1 because this is a C instruction. The next two bits are 1 1, which are reserve or spare. You can keep them 1, you can keep them 0. Then these 7 bits specify the computation. For m is equal to 1, the computation is 1, and from this table you can see that the 7-bit code for this field should be 0 1 1, 0 1 1, then we have 4 ones. The other 3 bits for the destination, and for this instruction m is equal to 1, the destination is m, and from this table we see the destination bits are 0 0 1, so we have 0 0 1 over here, and finally there is no jump involved, so the 3 bits for the jump field are 0 0 0. Okay, so this is m is equal to 1 hack assembly instruction, which is mapped to its corresponding 16-bit hack binary code. My dear students, follow the same steps, and getting the help of this table over here, you can translate this entire hack assembly program without symbols, of course, to this corresponding hack binary code. Please take a deep breath and let us start discussing the design of a 2-pass hack assembler that will take care of the symbols as well. So now we know how to deal with the white spaces and the comments, and we also know how to translate the A and the C instructions inside the hack assembly program. Now is the time to talk about symbols, which are shown in red color in this hack assembly program. Dear students, target is given as input this hack assembly program. We will sort all the symbols, and we need to translate it to this hack binary code. Well, if we see this hack assembly code, we can make out that there are 2 predefined symbols, R0 and R1, 3 label symbols, loop, stop and end, and 2 variable symbols, namely I and sum. Let us see how to handle the predefined symbols first. The predefined symbols occur only in A instruction, and we simply replace them with their corresponding values. So in this sample code, this at R0 will be translated to at 0, and this R1 will be translated to at 1. Let us understand how to handle the label symbols. Once again, in this sample code, these are the 3 declarations of the label symbols: loop, stop and end. And we all know that these are the targets of some go-to commands. So this label loop is mapped to instruction at memory address 4. Loop correspond to value 4. This label stop is mapped to instruction at memory address 20. And finally, this label end is mapped to instruction at memory address 24, as shown over here. As far as the translation is concerned, remember, label declarations are pseudo commands, so they generate no code and are not translated. However, they are used in the A instructions as highlighted over here: at stop, at loop, at end. Over here, of course, these symbols need to be replaced with their corresponding values which we have over here. Let us now see and understand as how to handle the variable symbols. And in this example code, there are only two variables, namely I and sum, declared at instruction number 0 and 2 respectively inside an A instruction. So as per the hack machine language specification, the first declared variable I is assigned the RAM address 16, and then sum is assigned the RAM address 17. As far as the translation is concerned, the assembler replaces all the occurrences of variable named I with RAM address 16. So this will be replaced with 16, this will be replaced with 16, this will be replaced with 16, and so on. And all occurrences of the variable named sum with 17. So this will be replaced with 17, this will be replaced with 17, and so on. Okay, dear students, I think I have once again set the stage right to understand the design of a two-pass hack assembler. But let me tell you again, as why do we need a two-pass assembler? Well, dear students, if you observe this sample hack assembly code, you can note that the assembly programmer has declared a label named stop just before the instruction number 20. Moreover, you can observe over here that the assembly programmer has used this label stop at instruction number 8 well before its declaration, and this is called forward reference. And to resolve a forward reference, we need to design a two-pass assembler, which is an assembler that go through the source file twice, called the passes. Well, the target of the first pass is to generate the symbol table. So before you start reading this file, you create an empty symbol table. Then you initialize the symbol table with all the 23 built-in symbols as already discussed in the hack machine language specifications. And remember, dear students, we are creating this symbol table so that later, given a symbol, we can look up its corresponding value. And if we talk about implementing this in C or C++, if you are a beginner programmer, you can simply use a linked list with a lookup time of a big O of n, and enthusiastic students can study another data structure called the hash table that can be used to map these symbols with their corresponding address values. And remember, the lookup time for this symbol table, if implemented using a hash map, will be big O of 1, that is constant time, irrespective of the number of entries in this symbol table. Anyways, once we are done with initializing the symbol table with these 23 predefined symbols, we will start reading this input file line by line. We will look for the label declarations only, and meanwhile, if we come across any A or C instruction, we simply increment a line number counter. So this 0, then we have 1, then we have 2, then we have 3, and then we have 4. At line number 4, here we have a label declaration called loop. So we put its entry in the symbol table, assign address of the next instruction, that is 4, to it, and move ahead. Next label declaration is stop. We place an entry in the symbol table with the symbol of stop and the value of 20, which is the address of the next instruction. And remember, The way we are moving ahead, reading every instruction, we are keeping a counter, and that is the counter which tells me that this stop, the next instruction after this stop is instruction number 20, and that is the value I have placed over here in the symbol table. And finally, the last label declaration is end, and it is at line number 24, so I have placed that value inside the symbol table. So the first pass is over, and this is the symbol table that we need for the second pass. And now let us start with the second pass. And by second pass I mean let us start reading the source file once again from the very beginning, line by line. The first instruction is at I, which is an A instruction with a symbol named I. Look for this symbol named I inside the symbol table. Not found. So that means this is a variable symbol, and this is the first occurrence of that symbol. Make an entry of this symbol I along with its value in the symbol table for future use. And remember, the variables are allocated in the RAM from address 16 onward as per the hack machine language specifications. Now we can easily translate this at I instruction to its corresponding 16-bit instruction. So we do that, and then we move ahead to the next instruction, and the next instruction is m is equal to 1, which is a C instruction, and we know very well as how to convert it to its 16-bit counterpart. So here is a 16-bit corresponding instruction to this assembly instruction, m is equal to 1. Let's move on to the next instruction, and that is at sum. Look for this symbol inside the symbol table. Not found. So that means this is the first occurrence of another variable symbol named sum. Make an entry of this symbol sum along with its value in the symbol table for future use. Remember, this is the second variable, so it has the address 17. Dear students, in our hack assembler, all variables are of 16 bits. Therefore, the addresses of the variables can simply be incremented, as I have done over here. The translation process of this assembly instruction at sum is again very simple. So this is an A instruction, so we have a 0 over here and 15-bit corresponding value of 17. And dear students, this process will go on. You will keep reading the instruction. If it is a C instruction, you simply translate it. If this is a symbol, you resolve it and translate it to the corresponding 16-bit instruction. Well, do note that this instruction loop over here, this instruction loop do not generate any machine code. Instruction at address 4 is being translated over here, and once this instruction will come, since we already have the symbol I over here, so no new variable is created. Rather, this I is simply replaced with 16 and its corresponding 16-bit instruction is generated in the hack machine language. So this is how we keep on moving ahead, one after another, one instruction after another. So my dear students, once after all these assembly instructions over here get translated to the corresponding machine code and get saved in a file with a .hack extension, we are done with the second pass of the assembler. Okay, so this slide shows all the steps that we as an assembler have taken in the previous illustrations. Dear students, please read it. This will make sense to you now. My dear students, if you have a bit of programming skills, writing a hack assembler in C or C++ will prove to be a piece of cake for you. And I am leaving this as an assignment. However, I will upload the executable file of a command line assembler named hasm written in C++ on the course Bitbucket repository. Okay, so that is it. I think this was the lengthiest session so far. I don't know whether you have listened it in one go or not, but I have recorded it in one go and feeling a bit tired. Maybe I have grown a little old. My dear students, I hope you have enjoyed learning this first half of the course with me as much as I did enjoy making it. See you in the next half of the course, which will deal with the assembly of x86-64 architecture. I hope the 25 lectures that I have delivered so far on the first half of this course were informative for you all. If you have liked them, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.